Okay, guys, so things are going to get a little bit complicated, but I will go slowly, okay? Um, so we are going to continue angle modulation. We will mainly talk about FM in this lecture. Like I said at the beginning, we will deal with phase modulation and frequency modulation, but when things get complicated, we will restrict our attention only to frequency modulation. But our main task here is to calculate the bandwidth of the tone frequency modulated signals. Remember in AM we did for the general signal of bandwidth B, but we also consider tone modulation, which means there is a single tone modulating the carrier. And when we want to calculate the FM bandwidth, we run into certain issues. So, but I have to tell you certain things. For example, one of the first thing is later on when we calculate the tone modulated frequency modulated signals bandwidth, we need to know the bandwidth of a single tone. So if you have only one tone message signal of frequency f sub m, we define the bandwidth as f sub m. Even though it is one spike at negative FM and plus FM, the spectrum, we consider the bandwidth as f sub m, because we have to make this this type of definition in order to calculate the frequency modulation, the bandwidth of the frequency modulated signal. So if you have two tones, like if you have more than two tones in the message signal, then you have to take the maximum frequency in the tone signal. See here, this has FM1, FM2, FM3. So you choose the maximum. Maximum will be the bandwidth of the message signal. Okay, this is very important. And here is an example. G1 is this sinusoid, and as you can see, it has frequency 350. G2 has 350, 700, and 500. So the bandwidth of the first signal is 350. Bandwidth of the second signal is the maximum of these two, which is 700, and then so the question asks state the bandwidth of the signal. So the bandwidth of the first one is 350. The bandwidth of the second one is the maximum of these, which is 350, 750, and 500, and the maximum is 700. And I have just illustrated it using a diagram. Okay, so if you have just FM, the bandwidth is FM. If we have different frequencies, of course this side I haven't shown, but the bandwidth of this signal is considered to be 700 Hertz. All right. Another thing is what happens when we mix two. Earlier at one of the lectures I told you when you have two sinusoids how to calculate the power. But now we have a situation where we have to calculate the peak value of sum of sinusoids, not multiplying, adding. Two sinusoids added, such as sine 100 pi t plus sine 700 pi t, and you can put some numbers in front. 2 sine 100 pi t, 3 sine 700 pi t. So there is a theorem, whenever these signals are orthogonal, you can just add the peak values. So if you have 2 sine and then 3 sine of different frequencies, you can just add the peak values. Okay. Now this orthogonal thing, you can do this whenever the signals are orthogonal, but in the first lecture I mentioned which signals are orthogonal. For example, a constant is orthogonal to cosine, constant is orthogonal to sine, and two cosine signals of different frequency, as long as f1 and f2 are not equal, they are orthogonal. Any cosine and any sine, they don't necessarily have to be the same numbers. Even if the frequencies are the same, they are orthogonal. Okay, so whenever you see this, if you need to calculate the peak value, you just add the peak value of the individual signals. Okay, so I think here is an example. Find the peak value of this signal. Okay, so it is 5 plus 4 plus 2 plus 3, and the reason is they are all orthogonal. This is orthogonal to this, this is orthogonal to this, this is orthogonal to this. Okay. By the way, I have started marking a midterm. I am marking it very slowly so I can give you a lot of part marks. And something I noticed is even when there is an exactly the same example in the lecture notes with numbers, exactly the same question with different numbers. That's the first question I'm talking about. Roughly half the people I have marked so far, they didn't have the correct answer, but I am giving part marks. Like this was an open book exam. You had the notes. How can you go wrong with that? Another thing is I have to give everyone 5% free marks. Everyone is going to get 5% because I made a mistake in, remember that bracket where I gave you the marks, each question is worth so many marks. There is one question that was worth 15%, but I mistyped it as 10 in some of your exams. Or maybe all of your exams. So the only way to resolve that is to mark out of 10 and then give 5% free. So everyone is going to get 5% free. And the other good news is, I mean, I don't like it, but it's good news for you guys. I think the class average is going to be low. So I'm going to, after I mark, I will add some marks to everyone. So everyone is going to get boosted a little bit, and I haven't decided how much, but I think I have to boost by a percentage. It's like everyone gets 5% more or 7% more or 10% more, so that I can bring the average to a decent level like 60 or 65. But what I am going to do is I will publish the feedback in D12. And in that feedback, I wouldn't add that marks, so because I want you to know where you went wrong. And I will enter the mark in the grade roster in D12 where it says grade later after I add the mark. Okay, so you will know your marks by Wednesday, but it's going to be increased by 5% because of the mistake I made, and then there will be some adjustment to bring the average. Okay, I'll send you a detailed email about that. What else about that? Okay, and then some of the questions are so simple, anyway, I'll explain some of the questions later after we finish frequency modulation. We have to do one more lecture on frequency modulation. And another thing is, I told you last week, we are not going to have a lecture this Wednesday. We will start next Monday. Okay, no lecture on Wednesday because I have a conference. I had to do a presentation. Okay, no lecture on Wednesday. But Monday we start again. And I will finish marking by Wednesday. All right. Okay, so here is another question. Let's see what is new here. I think this is exactly the same question as we did in the previous lecture. It just get copied here. Yeah, this is exactly the same. I explained this last time. We are using Carson's rule. This example is in the previous lecture as well. So we will skip that. Okay, so in the first day when we started angle modulation, I said FM, this chapter is going to go into so many different branches. There is general modulation, Sorry, first of all, there is phase modulation and frequency modulation. Then there is general modulation and tone modulation. Now you have another branch, narrowband angle modulation or wideband angle modulation. So essentially the problem is, I mentioned earlier last time, we really have to make wideband angle modulation. The wideband means the bandwidth is large, but it is very difficult to do that. So we actually make narrowband angle modulation and then use a technique called Armstrong's indirect method of FM generation to create wideband FM. And we want to increase the bandwidth of the FM, like we need to have wide bandwidth in order to suppress the noise. This is the main difference between AM and FM. In AM, as long as your message signal bandwidth is fixed, the modulated bandwidth is fixed. It is 2 times B. But in FM, you can have 1.5B, you can have the 2B, you can have 3B, 4B, 5B, you can have whatever you want. But there's a problem. You can only make narrowband angle modulation first. And how do we define narrowband modulation? Whenever this modulation index or deviation ratio, which is defined as maximum frequency deviation divided by the message bandwidth. Whenever this number is less than 0.3, we call it narrowband angle modulation. So what happens with narrowband angle modulation is, and at this point we will go to only FM. So remember, the FM wave can be written like this using the power series of e to the x. I went through this last time. And if this condition, remember these could be complex numbers. So this, I think at this point it is real numbers. So if the absolute value of this is much less than 1, then these numbers are going to be small, so we can start ignoring them. So what we do is, under this condition, we ignore the square term and the cube term, and FM becomes just this part and this part. So again, let's forget about phase modulation, focus on this. This is very important. For narrowband FM, which is defined as beta is less than 0.3, the modulated FM can be written as AC cos omega ct minus KF integrated message signal sin omega ct. And so we start with this, and then this will have a narrow bandwidth, but then we go through something called Armstrong's indirect method of FM generation and then increase the bandwidth, which will be the subject of the next lecture, Armstrong's indirect method of FM generation. Okay, but right now I want to talk about narrowband angle. And if you look at it, this looks almost like AM large signal, except for this plus. In AM large signal, this will be plus. There is no integration in AM, and in AM this is cosine, but now we have sine. Okay, that's, you need to observe that similarity. All right, I think now we are going to go to tone modulated FM. And here, after this page, we are going to use that handout I gave you about important reading before FM. There is Bessel's functions and stuff, they are going to come. Okay, so consider the tone message A sub m cos omega t. So we know the peak value is AM and the bandwidth is f sub m. We can easily note that. Now, when you integrate this A of t, remember A of t is the integral, which is, so this comes down, so AM over the omega m, and cosine becomes sine. So we know how the FM modulated wave looks like. It is AC cos omega ct plus KF A of t. A of t is the integrated signal. So I go here, and for A of t, I sub this in and I get this. At this point, I remember the deviation ratio in this case, the formula is kf m peak over 2 pi. We did this last time, deviation ratio. Now, in this case, peak value is a sub m, so I put that, and then using this and then at this point I write beta deviation. This is maximum frequency deviation. This is deviation ratio. Deviation ratio is this divided by b. So I sub in, but I remember b is bandwidth is fm. So it is del f over fm. At this point I go plug this in, and what transpires is kf m over omega m turns out to be exactly equal to beta. So for here I write beta. So in tone modulated FM, if you like, you can directly memorize it. A sub c cosine omega ct plus beta sine omega t. So we have the derivation here. So we can always start from here, tone modulated FM. And beta is the deviation ratio. And the tone is A, whatever the number you have, cosine omega mt. After integration and then some manipulation, if you want to write this in terms of beta, it becomes this. Okay, all right. Now, so remember, tone modulated FM, the equation is this in time domain. Now, we are going to look at the spectrum of this thing. This is where Bessel's function is going to come. Okay, so what do we do is, just like before, we write a complex number whose real part is this. So we make up this complex number, which is a sub c e to the j omega ct beta sine omega mt. And then we split it into a sub c e to the j omega t times e to the j beta sine omega t. And then we remember in that lecture, this is the lecture before the midterm, I showed you this e to the Fourier series of e to the j beta sine omega t can be written like this, where the coefficients are Bessel's function of the first kind and order n. In other words, the Fourier coefficients of these functions are Bessel's functions. So for exponential Fourier series, this is exponential Fourier series, not trigonometric Fourier series. The frequencies, okay, here, if you like, you can write 2 pi fm. But you see the n, it starts at negative infinity and goes up to plus infinity. So it is like a little bit like you will have the frequency 100 times fm, but it negative 100 times, negative 99 fm, negative 98 fm, and then it comes negative 3 fm, negative fm, 0, then fm, 2 fm, 3 fm, and so on. And then for each one of them you have the Fourier coefficients, but the Fourier coefficients are the Bessel's function. So I go plug in here, and then what did I do? I pull out bring this inside, and I get this. And then at this point I take the real part. So I go back. This is the real part of this. And the real part of this is a sub c, sigma, and j and b. Those are real numbers. And out of this is e to the j cosine something plus j. Sorry, this is cosine j something plus j sine something. So the real part is only the cosine. And this is very important. Now this looks like a series of AM modulation or DSP-SP's spectrum, because I mean we don't even have to go there. Look at this. This is cosine omega c plus n omega m. So this spectrum is going to be centered at Fc, and then you will have two spikes at Fc plus Fm and Fc minus Fm. Then another one at Fc plus 2 Fc and Fc minus 2 Fc. Cn can be negative and so on. And the coefficient or the amplitude of the spectrum is, because from the modulation theory before, Fourier transform. Fourier transform of cosine has a half in it. So it is a sub c over 2 and then Bessel's function. And also the table only gives you the values for positive n. So for negative n, it is actually negative 1 to the n j and beta. We have to use this, and I'm going to show you a picture. I know this looks complicated, and also usually I would only ask you the magnitude of the amplitude of the spectrum, so I wouldn't worry about putting a negative number there. Even though it is, the spectrum is negative, I am only looking at the magnitude. So let's go here. So this is how it looks like, and I have ignored the negative thing. This is the magnitude spectrum. So when you are doing tone modulation in FM, and if the signal is cosine omega mt, remember that's how we started, cosine mt. I want to show you again. Yes, your message signal is cosine mt and there is some number there. It changes into this, and we always start with this. In order to calculate the bandwidth, you need to know the beta. Once you have the beta, the spectrum looks like this. Okay, and once again you can see the Bessel functions keep on going. So theoretically the bandwidth is empty, but importantly the Bessel numbers, after a while, the accepted custom is when it is less than 1% of the highest number here, we start ignoring them. So let me show you the table first. Yeah. Okay. So you need to know the beta first. Look at beta is equal to 0.4. Okay. These are the beta values, by the way. See here, this is beta. And here it is the order. So J0 for 0.4 beta is 0.96. J1 for beta is equal to 0.4 is 0.2. Then it is 0.02. Then it is all zeros. Okay. So the theory, this is not exactly 0, but it is a really tiny number, less than 0.01. Look at what happens when beta is 0.8. J0 is 0.85, 1 is 0.37, then 0.08, 0.01, and then it is 0. So when we calculate the bandwidth of tone modulated FM, one of the accepted rules that we use is neglect the spectrum when it is less than 0.01. So it is given as 0 here anyway, and that is called 1% rule. So what is 1% rule? Basically throw away, don't talk about the zeros. Well, it is very obvious. Okay. So, and then it is always important to, like, don't worry about any of those things. Just remember the picture. Okay. This one. Also, I think before the exam, I told you guys, if you want to write, if there is a question about AM bandwidth, don't write those delta functions. Just give me the numbers. Okay, because it takes a long time to write. Okay, so look at how FM bandwidth looks like. It is very important that the Bessel's numbers are multiplied by AC over 2. So that's what I say here. Okay, so when I actually ask you what is the amplitude of the spectrum at FC, it is not J0 beta, J0 beta times AC over 2. Okay, remember that. Another thing is, there is the mirror image of this on the other side. Okay, and I haven't drawn this. It's not just FC, it is also at negative FC. Alright, so I'm going to now show you an example of how to calculate a big question. Okay, so a tone of frequency FM is frequency modulating using the carrier 7 cos 2 pi FCT with beta is equal to 0.4. So beta is given. Find the amplitude of the tone modulated spectrum at Fc plus Fm. Then find the bandwidth, the modulated signal using the 1% rule. And then find the bandwidth using Kandasamy. Okay, all right. So the first question is beta is given, A sub c is given, and the amplitude of the spectrum at Fc plus Fm. So if you look at the diagram, at Fc plus Fm, the amplitude is J1 beta. J1 at beta. So AC over 2, J1 at beta. AC over 2, J1 at 0.4 because that's given. So we have to find J1 at 0.4 and multiply by 7 over 2. So let's go to the table. J1 at 0.4. Beta is 0.4. Where is 0.4? 0.4 is here. J1 is 0.20. See J1. Okay. 0.4 is the beta. J1 at that point is 0.20. So I should have plugged in 0.20. 0.30 times AC over 2 and then I get the answer. By the way, another thing I want to tell you is in the exam for the midterm when I am marking, if you made a careless error in the computation, I am not taking you any marks off. I gave you the full marks. As long as your steps are correct and you set up your equations correctly, I am giving you the full marks. Okay. Bandwidth of the modulated signal using the 1% rule. So what we need to do is go there and look at for beta is equal to 0.4 and check when does the spectrum dies down. 0.4, beta is 0.4. There is J0, J1, J2. After that we don't see anything. So 1% rule means anything less than 1% you throw away. So the last spectrum occurs at J2, J2. And when does J2 comes? Fc plus 2Fm. So the band, so you are going to have 2 spikes here and 2 spikes here. Nothing here because after J2 it is 0. So from here to here it is 4 times F sub M because this is 2Fm and this is 2Fm. So let's go see. So it is 2 times 2Fm. Okay. Let me explain that again. It is we are at beta is equal to 0.4 and we are looking at 1% rule. Beta is equal to 0.4 and we have this is at the Fc, this is at Fc plus Fm, this is Fc plus 2Fm. So 2Fm this way, 2Fm this way, 4Fm. Okay, that's it. 4Fm and we don't know what Fm is. That was not given, right? Yeah. Now, when we use Kandasamy's rule, we can use this one formula. 2 times the message bandwidth times beta is 0.4 and we sub in and we get 2.58 FM. Now, don't be alarmed that we get such widely different answers. Remember, Kandasamy's rule is an estimate. So sometimes these don't agree and don't worry about that. Alright, I think there may be another example. Okay, now here we have a more complicated example, slightly more complicated. So in this case, message signal is this. So what do we know? The A sub c is 2 and the frequency FM is 1000 Hertz. Find the frequency modulated signal if the carrier is this and KF is this. So here I have derived that, but if you want, you can directly go and plug in. You can always start with this equation if you can calculate beta, but maybe that's what I did. So let's see. Okay, so message signal is this, integrated signal is this because this comes and divides here, and then I have to put KF in front. So phi FM is 5, this is omega c is given. Yeah, where is the, yeah, 2 pi 10 to the 8 t, 2 pi 10 to the 8 t plus, then I just copy the integrated signal here. And then I have simplified this, and it is 5 cos this plus all of this get simplified. This pi and this pi cancel and then end up with this. Now I compare this with this one and realize beta is 2. So I have all the information I need. I have A sub c, which is 2. Frequency of the message signal f sub m is 1000 Hertz, and I have the beta. So the first question, I have found the frequency modulated signal, the time domain signal. I have found the deviation ratio. Find the amplitude of the modulated spectrum at 10 to the 8. Remember, 10 to the 8 is the frequency of the carrier, Fc plus 1000. 1000 is the bandwidth of the message signal. So that means they are asking Fc plus Fm. What's happening at Fc plus Fm? They are asking for this value, which of course is J1 beta. And what was our beta? I forgot what our beta is. Our beta is 2. See, beta is 2. So now I go to the Bessel's table, and remember beta is 2, and they are asking the amplitude of the spectrum of the modulated signal at Fc plus Fm, because 1000 is Fm. See here? Alright. So Fc plus Fm, which must be J1. Let me show you the diagram. At Fc plus Fm, we have to look for J1 at beta, and beta is 2. So where is beta is 2, which is here, and J1 is 0.58. But remember, all of these values have to be multiplied by AC over 2, A sub c over 2. So A sub c over 2, and A sub c is 2. So it's 2 over 2. Do I see 2 over? Oh, sorry. That's the message signal. Sorry, I keep saying carrier signal is here. So sorry, this is not AC. A sub c is this, which is 5. So 5 over 2, and then the value from the message table, which is 0.58, because beta is 2. So AC over 2, and then J1 at 2. Let me show you J1 at 2 again in the Bessel table. J1 at 2. So where is 2? 2 is here. J1 is 0.58. Okay, this is J0, this is J1. Okay, so that finishes that part. We have calculated the amplitude of the spectrum at this point. Then they are asking Fc minus 3 times Fm. Remember, this is Fm, this is 3 times Fm. So we have to look at J3 and calculate J minus 3. So, by the way, they ask for the amplitude. So I may have just given the positive value. What am I doing here? Okay. And since this is, I am just asking the amplitude, I put an absolute value, so I don't have to worry about the negative thing. Like I told you in the exam, I'm not going to worry about the negative. I will ask you the magnitude of the amplitude. Okay, spectrum. So AC over 2, J3 at 2. Oh, so we have to look at J3. J3 at 2. J0, J1, J2, J3. J3, see here, J3 at 2 is 0.13. 0.13. Let's see if we have 0.13. 0.13. Yes, 0.13 times AC over 2. That's it. Forget about this negative and all of that. Okay, I'm only going to ask you the magnitude of the amplitude spectrum. Now then the next part is find the bandwidth using the 1% rule. So for this beta value, which is 2, remember beta is 2, we go to the table and check where they die down. Beta is 2. Beta is 2. Okay, so we have beta is 2. Keep going. Oh, I need to go a little bit more. Beta is 2. Keep going, keep going, keep going 1%, and it dies here. So it goes up to J5. Remember, it starts at 0. 0 is FC, FC plus FM, 2FM, 3FM, 4FM, 5FM. See here, 1% rule. After that, it is 0. We add beta is 2. Beta is 2. It dies down after 5FM. So there is 5FM this way and 5FM that way. We should have 10FM. Okay, see this number is 5, 4, 2. Okay, after that it is all zeros. So okay, I should have written FM here to be more clear, but I have put beta. Okay, and 2 times 5FM. Okay, 2 times 5FM. And what is FM? Where is our message signal? Our message signal is here, and it has frequency 1000 Hertz. So message signals bandwidth or FM is 1000. It would be more appropriate to write FM here. So if you wish, please cut this out in your note and write FM. There is nothing wrong here. The bandwidth is still 1000 Hertz. Okay, so 2 times 5 FM. Okay, 2 times 5 FM, and this is all right. And the next question is calculate the bandwidth, estimate the bandwidth using Carson's rule. So to use Carson's rule, actually I don't need this calculation. I could have used beta here, right? But I first calculate del F and do this. I think a faster method is to use that 2 beta formula. There is a formula with beta in it, right? Which one we used? Yes. 2 bandwidth times beta plus 1. So beta in that question is 2. 2 plus 1 is 3. So it says 6B. 6B. Let's see if we have 6B. 6B and B is 1000, so it is 600. So we get 6000. We get the same answer. This calculation is unnecessary. And I am doing this and then arriving in, but anyway, we get the same answer. So you guys may want to use beta. Beta is 2. Beta plus 1 is 3. 3 times. And then what? There is a 2 in the formula. So 6. Yeah. 6B and B is 1000. So it is 6000. Okay, guys. So let's see if you know what? Totally ignore this. I'm not going to go into this. I am totally aware that this is an accelerated course, so please ignore section 6. Basically what happening here is there is a similarity between the tone modulated narrowband FM and the AM large carrier. Okay, and I am not going to examine you on this, and it's not just it's not really useful anyway, so please ignore 6. Section 6. Please ignore 6. Okay, guys, so that's it.